Hello everyone, and welcome to the second video in the series where I try and go through what is the equivalent of an intermediate level undergraduate electricity and magnetism. Last week, I kind of went over the basics of, what vectors are and some of the basics of vector algebra, how to manipulate them, add, subtract, the different kinds of multiplication you can do on vectors. And today we're gonna kind of continue that by going over the basics of vector cal or going over some of the important points of vector calculus. How to take derivatives on them, how to take integrals, the different important theorems and properties you have with vector calculus. And these will become very important when we start going through some of the actual, electrostatics and magnetostatics theorems, as you'll see in future videos. So, without further ado, please enjoy. And so to start, let's move over to my whiteboard, and we are going to start with a little crash course slash review of calculus, just normal non-vector calculus. If I can pull up. There we go. Now I can see. All right. So, give me pen. There we go. All right. So, let's start with some algebra. So, something that is very fundamental to algebra. If you remember, whenever you have a line, you can express a line in the form y equals mx plus b, where we're going to focus on this m. This is... Oh. This is the slope. This tells you, in essence... Yeah! Alright, this tells you, in essence, how steep or shallow your line is, right? If m is greater than 0, then that means your line is going up. If m is less than 0, your line is going down. And the larger in magnitude, or the larger in absolute value the slope is, the steeper the line is. And so the way to calculate it, this quantity in algebra is rise over run. The change in your y value over your change in your x value. So, why am I talking about algebra when I said we were doing calculus? Because calculus, or at least calculus, has two important components. The first is a derivative. So a derivative is the instantaneous slope. So instead of looking at the average slope between 2 points, you care about the slope at a specific x value. So what that means is, let's say we had some arbitrary function that's not a line, so maybe something like this, right? And you want to find the slope exactly at this point. Well, in algebra, you'd have to take 2 points, say here and here, and find the average slope, but that's not always accurate. Oh, is it? Thank you. Alright. Oh no, the immersion. Alright, so to calculate this instantaneous slope, we take this rise over run and we do some calculus magic that I'm not going to go over right now because that's more math than physics. I just care about trying to convey what the derivative does. So this becomes dy dx. And this is what's called a derivative. This d, instead of the delta, represents what's called a differential, which corresponds to an instantaneous. That's all. That's the important part, at least. Um, the other important part of calculus, the other half of it, is integral calculus. So once again, we're going to talk about the algebra. Why aren't you... there we go. Maybe that'll work now? Oh, okay, yeah. Sorry, this is my first time trying to use multiple pages on this. All right. So, integrals. So, in algebra, let's say, let's say you had some constant function like this, right? This is just y equals some value a, some constant value a. And you wanted to find the area between this function and two values x1 and x2. Well, this is a rectangle, height of which is a, length is the difference between x2 and x1. So that area is a times x2 minus x1. And if you wanted to find, all right, and if you wanted to find, say, the area of a more complicated function, what you could do to kind of make an approximation is, let's say I have this weird function again. What you could do is take small rectangles. Yeah, so like there, there, and so on. So as you can see, because it kind of underestimates and overestimates the area in some places, it's only a guess. It's an approximation. In that case, the area becomes a sum. So this is the Greek letter capital sigma. This just means whatever is here, you add over. So this would be the value of xi times delta xi. And I goes from 0 to however many rectangles you take. So this means you start at x0 and you just add this up until you get to x sub n. So, but that's just a guess. If we want the exact area under this curve, again, you do some calculus magic, and this actually becomes the integral from x1 to x2 of your function dx. And as you can see, you can kind of tell it's the same thing because you have the f of x here, your height of your rectangle, times your length, your width. In this case, it was delta x. In this case, this is dx. And because, like I said, this is an instantaneous change, a very, very, very small change in x, this will end up summing over the tiniest slivers of rectangles. So it'll end up giving you a much more accurate value for the area. So again, don't focus too much on, actually how to calculate these things. The important part is if you want to know the instantaneous rate of change of something, you take a derivative. You want to know the area under like some curve, you take an integral. So yeah. So, how do we incorporate vectors into this? Well, first, we have to show what a vector field is. So a vector field, instead of just having one vector, right? Like last time where we had, you know, some arrow pointing some direction. Instead, you're going to have uh you're going to have some vector A is going to be dependent on x, maybe y, and sometimes z. That means that your each component, so A1 becomes a function of x, y, and z. A2 is also a function, and so on. And so what this looks like, and actually, this is what I was prepping. Oh, sorry, my chat on my phone timed out. Oops, sorry, Cyrano. But yeah, so you take the integral. So yeah, let me pull up. Yeah, all right. Can you guys all see that? Not this specific diagram I have up, but the window. All right, yeah. So this is an example vector field. Let me shrink this a bit. So this specifically is the vector field representing the equation vector equals x hat plus y hat. So what that means, let me shrink this some more. Hello. How are you, Tyler? No, because I want to make this bigger. Okay. So what this means is that as you increase in x, the x component of your vector will get larger and larger. Oh. Oh, thank you for the sub. Yeah. That scared the shit out of me. I did not know it was going to make that sound. But thank you. So yeah, and so as you increase your y value, the y component of your vector will increase. So you end up getting a vector for every xy point in your area. So that's what differentiates a vector field from just one vector. All right. So, why did I bring that up? So, that's because when you're talking about vector calculus, you have to take into account more than one dimension. Yeah. So, instead of just having one derivative like we had in normal calculus, in normal calculus we just had df dx. Since you have more than one variable, you have to define what's called a partial derivative. And that looks like partial f partial x, partial f partial y, and partial f partial z. What that means is you take the derivative of f with respect to x. So you take the change of your function over a change in the x variable, but you keep the other variables constant. So this means y and z are held as you just pretend that they're numbers. Same with y, ddy, and same with ddz. And so with these partial derivatives, I mean, you can take notes if you want. I would be concerned, though, given your job, that yeah, I'm sure it's fine. Actually, yes, this will be on the test. At the end of all of this, I'm gonna have you guys build a laser, and if you don't blow up, then you pass. How about that? All right. So, with these partial derivatives of x and y and z, we can do some interesting things with them. The first object we can make is called the gradient. So if I have some scalar function, so that means just some number is a function of x and y, or some number is a function of x, y, and z, then the gradient of, let's take w, is partial w. Oh. Oh. Thank you, Spatial Notes, for, is that follow? Yes. Thank you. Out of curiosity, were you, just wandering around, Twitch, or? Caffeinate. Thank you. Unfortunately, I don't actually have caffeine with me. I have a protein soda, but the sentiment is appreciated. So yeah. So the gradient is defined as partial w partial x x hat. So partial plus partial w partial y y hat plus partial w partial z z hat. So that means that this gradient spits out a vector. It takes a scalar function and spits out a vector. And so, okay, what does this weird upside down triangle operator actually mean physically? What does it represent? So, similar to how a normal derivative told you the instantaneous slope of some function, the gradient tells you the area of greatest ascent in like a 3D graph or an n-dimensional graph. So for instance, if you had like some hill, right? Some geographic terrain, the gradient would tell you where in your where in this hilly area is it steepest. Where does it get higher faster? Um, and so I'm actually going to exemplify this by actually doing an example. Um, I gotta pull up the example. There we go. Okay, so let's say we have a hill, right? And the height of this hill, um, as a function of x, which is we'll define as feet, you move east, and y is the number of feet you move north. Well, the hill's height is defined as 10 times 2xy minus 3x squared minus 4y squared minus 18x plus 28y plus 12. I'm sorry, this is a ridiculously long function, but this was the example I found. So, we want to know where the top of the hill is. Where is the summit? Well, the summit is going to be the point, the highest point, right? So, if you go back to 2D, right? And you look at something that just goes up and down, right? So everything on this left side is going to have a positive slope, right? And everything to the right of it will have a negative slope because it's going down. So that means that the highest point will be where the slope is 0. Oh. Is it showing? I didn't see it. Okay. Nep, you might have to help me with that then, because I thought I did it right. I don't think it's covered. Yeah. Yeah. I didn't know there were extra steps to that redeem. I think I just fucked it up when I set it up. Scuff. Sorry. Uh, yeah. Okay. So yeah. So that means that if we want to find the summit, that we need to find the point where the derivative as respect to x is 0, the derivative with respect to y is 0, and the derivative with respect to z is 0. Otherwise known as where the magnitude of the gradient, or h in this case, the magnitude of the gradient is 0. So let's first calculate the gradient. Again, follow along if you can, if you have the prerequisite knowledge. Otherwise, you can just listen. So the derivative with respect to x is going to be so 10 times 2y minus 6x minus 18 x hat plus 10 2x minus 8y plus 28 y hat. Alright, I'm gonna leave this. Alright, and so the magnitude of this vector is going to be, again, if you remember from last week, the magnitude is, again, using Pythagorean theorem. I really need to find a way to just pin the Twitch chat to the, so it always stays like up front of my monitor, but I don't know how to do that either. So the magnitude is the square root of these components squared. So 10 2y minus 6x minus 18 squared plus 10. No, sorry, bracket goes here. 10 2x minus 8y plus 28 squared. So that becomes 10 times the square root of 2y minus 16x minus 18 squared plus why is my brain blanking? 2x minus 8y plus 28 squared. So, and we want this to equal 0. So that means we can divide this out, square this, and we get 2y minus 16x minus 18 squared plus 2x minus 8y plus 28 squared equals 0. Statistics is, well, you can make it math, but for the most part, non-mathematicians don't need to use the math part of stats. Fuck. Okay, sorry. So this becomes 4y squared minus 32xy minus 18 times 2 is 36y. Fuck. Actually, sorry. Sorry, I didn't have the time to work this out before stream. But like I said, I want to focus more on the physics. So the specific math, I kind of leave as an exercise. Sorry. Um, but yeah, but that's how you would solve it to find where the summit is. And then you can plug that point back into the initial function to find out how tall the hill is. So yeah, that's how a gradient works. That tells you how steep your function is. So what we can do, if we have some function of x, y, z, and that equals partial f partial x hat partial f partial y hat plus partial f partial z, then what we can kind of do is we can take this f out and treat this gradient as an operator, a set of instructions that when it is acted upon a function, it tells us what to do. So we'll call this the gradient operator, and that's equal to just the derivative operators. Yeah, partial y hat. So I stress that this is an operator. And the reason I stress that is because while delta on f is defined, f on delta is not a true vector. That would give you just another operator. So, with this gradient operator defined, now we can talk about how to take derivatives of vector fields themselves. So, if I had some vector field, so let's call it E. So E is a function of x, y, z. So that means each of its components are a function of x, y, and z. Then if you remember from last week, there are two multiplications we can do on vectors. We can do the dot product and we can do the cross product. Well, if I do the dot product of the gradient with my vector field, that is called the divergence. Of E. And it is defined as, again, like the dot product, right? You multiply the x component of this with the x component of that, plus the y component product. Oh, yes, Kolak.
Has you really been far, even as decided to use Even Go Want to look more like? Call 985-655-2500 and
I'm guessing, yeah, that one didn't work either.
Go further and even more decided to use. You can really be far as decided twice as much to use and go wish for it. When you decide
All right,
far,
I'm going to take this opportunity to write out the rest of it.
Really far, even as decided to use and look more like and go after. It's just common sense. Apply today.
All right. All right. So, like I said, so the divergence of E is you take the x derivative of the x component of E plus the derivative of the y component of E with respect to y plus the derivative of the z component with respect to z. And so again, remember that divergence takes two vectors and outputs a scalar. So this is just a number, or in most cases, just a scalar function of yeah. So next we have the what happens if we take the cross product. Stop pressing the button. Okay, del. No, stop it. Del cross E. This is called the curl of E, which has a much more complicated formula, and I'm not going to go into it. You can look it up if you want. So, what do these actually tell us about a vector function? That's what I care about. So, the divergence of E tells us how quickly a vector function would spread out from a given source or converge to a given source. Either what otherwise called the divergence tells us whether or not some vector field has a source or a sink. And what I mean by that is, if we go back to this example, as you can see, all these vectors point away from the origin. So that means that this origin is our source of the vectors, the vector field. So if I were to take the divergence of this, I would get a non-zero number because it has a source. In contrast, if I had a vector field like this, as you can see, these vectors aren't necessarily pointing away from the origin, they're just simply rotating around it. So that means that since they're not spreading out, the divergence would be 0. But the curl tells us, like the name suggests, how rotational the field is, right? So if we took the curl of this vector field, it would be non-zero. And if we took the curl of that first vector field, it would be 0. And so again, because these are products, similar to how in normal calculus you have product rules, so do you with these. But because there are different types of multiplication, that gives us 6 product rules, and I'm not gonna go over them right now. I'll introduce them as they come up in the physics part of this. But one specific example or one specific operator I do need to talk about is called the Laplacian. I'm gonna go to here. The Laplacian a vector field is a vector field is like what I have up right now. For every point in your xy, for every point in your xy plane, you have a vector defined there. So instead of just having one vector, you have a vector for every point that you care about. Um, that's what a vector field is. Um, so yeah, so the Laplacian is defined as del squared of f, and that is simply the second derivative.
Gaussian, you have another screen up.
Oh, yes, thank you. Is it not fixed? I thought I fixed it. No, I fixed it. Which letters? Laplacian? Yes. Sorry. If you're looking at okay, yes. Thank you, Astral. If you're talking about Nep, if you're talking about this is a Greek symbol. That's not a letter. Oh, sorry. Okay, yes. Then that is my handwriting. I apologize. Let me try and write it out clearer. That is Laplaci, the Laplacian. And so that tells us the rate of change, of the first derivative, uh, with respect to the different variables. This one's a bit more abstract to explain. What am I writing with? My drawing pad. Sorry, no, this has nothing to do with the drawing utensil. This is just my handwriting. I'm sorry. Um, and so the reason I bring up the Laplacian is because there are certain properties of vector products that I want to talk about. So if I were to, or second order properties that I want to talk about. So if I were to take the curl, oh, trust me, you would not be the first one to try. They have all failed. If I were to take the curl of a gradient, that is always 0. You can do the math to figure that out, but it's 0. Proof by just trust me. And the divergence of a curl No, I'm saying my handwriting is written in stone. I have tried to fix it for as long as I've been alive. So this is also 0 with another proof by trust me. And then the curl of a curl, if you use the various product rules, is equal to the gradient of the divergence minus the Laplacian of V. Or sorry, I'm looking at the book accidentally. Sorry. The Laplacian of A. Since the Laplacian... Yes. Yes, Astral. So the way it was taught to me is like it tells you whether or not a vector field has a source or a sink. If you think about uh like a kitchen sink, right? As water drains from it, all the water will move towards where the drain hole is. So that means that that all the if you draw an arrow for all the water molecules velocities, it would all be pointing towards the sinkhole, the drain. And um, in contrast, like an explosion, right? All the pieces move away from the point of explosion. That would be a source. Um, yeah. So the divergence and curl are the important things, and these right here are the main things that I wanted to cover with differential vector calculus. Um, Before I move on to integral calculus, are there any questions? Again, I'd like to reiterate that my goal is not necessarily to get you to understand the intricacies of the math part of this. Um, I'd like to get you at least familiar with the notation and these quantities so that when they come up when I start talking about E&M, they're not like at least you've seen them at least once. And if necessary, again, I'm recording this. I'm going to end up posting this to my YouTube channel. You can always have the VODs to refer back to. So yeah. All right. No questions. All right. Cool. I will move on to integral calculus. So, sort of how differential calculus, because we moved to 3 dimensions, it gave you multiple kinds of derivatives you can take. Moving to 3 dimensions and including vector fields also gives you multiple integrals. So there are 3 main integrals that we care about in 3 dimensions. You have line. You have line integrals, surface integrals, and volume integrals. So a line integral, let's start with line integrals. A line integral, if you have some vector field v, right, and it's a function of x, y, and z, then the line integral is the integral from point A to point B, keeping in mind right now that these are 3-dimensional points right now, of v dot dl, where L is a specific path, right? So, I don't know how to annotate, but okay. So if I had, let's say, some vector field that did this, the line integral would add up all the contributions from these vectors over a given path. For instance, this path, right? So that's important. For instance, actually, this is good because I can mention a physics example, right? So for a physics example, work is defined as the line integral from A to B of the force over a given path, right? If you push a block, right, with some force F, then the amount of work that you exert on this block is going to depend on the path you take, right? So this is a lot longer of a path than just going straight through, right? So that's going to give you this path, let's call it path, let's call it path 2 and path 1. So path 2 is going to give you a much smaller line integral than path 1 because this L is a lot shorter. So that's what this line integral tells you. If you have some vector field, this allows you to add up all the contributions over a given path. And so if that means that also means that your path can be closed. And what that means is your path can end up looping back on itself, right? So your starting point is the same as your end point. And the way we write that out is we drop the limits, a and b, and we just draw a circle over the integral. That tells us that this is now the line integral over some closed path. And this will become important later when we go over like the properties of these. So, next, surface integrals. Yeah. Okay, so surface integrals are almost identical in function to line integrals, but for 2 dimensions. So, for S, if I have some vector field that's a function of x, y, and z, then the surface integral dot dA. Then the surface integral adds up all of the contributions over a given surface area. So, this is hard to show in 2 dimensions, but if you had some 3-dimensional vector field, you can draw. What's a good example for this? So if I had, yeah, okay. So let's say I have a vector field that's entirely comprised of this column of lines, and I want to know how many pass through like a rectangle, right? So this would be useful, for instance, if I have some window, right, and I throw a bunch of like tennis balls through it, right, and I want to find out how many, and I want to find out, how many pass through the window, right, depending on like how big the window is or how many I'm pushing through it at a time. Then what I can do is I can assign a vector to this surface area. Call it dA. This vector is going to be defined as being perpendicular to the plane of the surface, right? That's a bit mathy, but that allows you to take the dot product with the vector field itself and then add up all the contributions that pass through this surface. So that's useful when we're talking about things like flux, in which in physics flux just is defined as how many of a given vector field pass through some surface that we care about. That is going to be very important when I talk about Gauss's law, because this is the beginning of where my name comes from, Gaussian surface. But I will save that for a later date. So again, similar to line integrals, you can also have what's called a closed surface. So as you can see, we have this rectangle. If instead I chose the surface of a sphere, if I pick any point on the surface of the sphere, I can define a path that loops back around to the same point, right? Without ever lifting my pen, so to speak. As opposed to this rectangle, if I move to the edge of the rectangle, I could just straight up leave the surface of the rectangle. That's not possible on a sphere. So that's what we define as a closed surface. And so if we're integrating over the closed surface, then similar to the line integral, we just do that circle dot dA. All right, we're almost done. And I'm out of pages. What to do? Actually, you know what? I'm going to do this. There we go. Yeah. Yeah, we're getting close, okay? Like, this is going to be the last math lecture, fortunately. Every other math tidbit you need, I'm going to introduce as I talk about the relevant physics concept, because I really want to move into electrostatics next week. Because, again, I'm a physicist, not a mathematician. Although I did do math in undergrad. So, last but not least, we have volume integrals. Volume integrals are much, much simpler to explain. If we have some multidimensional function, right? It's not a vector field, just some you take your 3 points, it spits out a number. That's more of a math question, with regards to whether or not a surface is closed or open. but I believe it would be an open surface because so a closed surface is that all paths must remain on the surface. But for a Mobius strip, right, if I went perpendicular to the strip, I would eventually hit the edge. Basically, a rule of thumb is if your surface has an edge, it's probably open. I can't think of a counterexample off my head, but again, I don't want to say with certainty there might be a counterexample. But yeah, at least in physics, you can pretty much be confident that if your surface has an edge, then it's an open surface. So, if I have some scalar function, the volume integral, I just integrate it over a three-dimensional volume. Similar to in one dimension how we integrated over the area under a curve. This would just be integrating with respect to... oops. Let me redraw that. This would be integrating with respect to x, y, and z simultaneously. That one, again, fairly straightforward. Don't have to worry about vector stuff. All right. Any questions about just what those integrals do? Again, I'm not going to worry about how to calculate them right now. That I would rather leave to a mathematician. That's not where my interests lie. All right. Okay. So, last nerd thing I want to talk about tonight. The properties of all these calculus things. So, sorry, I need to find the right page. Yeah, okay. So, let's say we have a gradient, right? So, if I take the gradient of f, that equals partial f partial x. Yeah, we've seen this before. If I were to dot this, since this is a vector, with some specific path L, then this would equal df dx dx1 plus partial f partial y dy1 plus partial f partial z dz1. For mathematical reasons, this is what we call a total differential, which we denote just with df. So, if we wanted to say, take the line integral of this gradient over this path, del f dot dl, well, I can use this equation. That just becomes integral from a to b with respect to f. Do you have a question, Tyler? So, the one bit of integral math I will teach you is This is basically the integral of 1 df. Well, the integral of a constant is just the variable. So this would end up equaling f defined at point B minus f defined at point A. Ah, okay, good. Yeah, sorry. So, for a bit of context, so while I do have a lot of experience tutoring, um, because sometimes I don't know whether or not I'm going too fast, I will stop from time to time and ask if everyone understands. It's a lot harder to gauge an audience that you can't see the faces of. So, yeah. Um, again, feel feel completely free to stop me if I've glossed over something. Um, yeah. So, if you'll notice, this integral ends up just equaling f at point B minus f at point A. We did not define a specific path. It could have been the squiggly path, or it could have been the straight shot. It does not matter. So, what that tells us is two things. One, this integral is what we call path independent. It does not, you don't have to define a path. All paths, this integral over all paths that start at A and end at B are exactly the same. Which makes things very easy because you don't actually have to parameterize the path. You don't have to turn that path into math. Accidental rhyme. The other consequence is, like I said, a line integral can be closed. If I have a closed path, then my start point is exactly equal to my end point. So if I take the closed line integral, that looks like an E. Sorry, let me clean that up. The closed line integral is going to be f at A, because that's the end point, because we're stopping where we start, minus f of A. That is 0. The closed line integral of a gradient is 0. We love zeros. It makes things easier. So, those are the two consequences of taking the integral of a gradient. The other theorem I want to talk about... Oh, there's two more. The next one I want to talk about is what happens if I want to take the volume integral of a divergence. I probably shouldn't use V if I'm taking the volume integral. Let's do A. Well, the volume integral of this ends up equaling the closed surface integral of A dot dA, where this closed surface is defined by this volume, right? So if I was taking the volume integral over a sphere of a divergence, then that equals the surface area over the surface area of the sphere. So technically speaking, this is why I say the edge trick for determining whether a surface is closed is kind of a rule of thumb, because a cube, the surface area of a cube, is in fact closed. So if you have a surface area defined by the boundary of a volume, that is closed. So this. And so this theorem is called one of two things. You can either call it the divergence theorem, because the divergence, or Gauss's theorem. I did not make it. I did not prove it. This is actual Gauss. Actual Gauss is way smarter than me. I know, I'm teasing you guys. I'm teasing you. I want to build it up. I'll get there. I'll get there soon. It's a lot closer than you think. Well, okay, I know you know where it is, Astral, but it's a lot closer than the rest of you think. Getting to Gaussian surfaces. Alright. Last integral theorem. We need to talk about curls. This just means theorem 3. How did they come up with this? By being very smart and proving it. So mathematicians have various ways to prove things. All right, I'm gonna do a side tangent because I do have a dual major in math, so I did take these math classes. I'm just, to be transparent, I did not do nearly as well as, like, I passed these classes. They did not come nearly as easily to me as physics. There are various proof methods that you learn in the field of mathematics. The first one is direct proofs. That just means 1 + 1 = 2. You do the math. This just means you do the math, and it comes out correctly. You have proof by induction, which is, let's say, for instance, you have an is true for n equals 1. Okay. If I prove that if some arbitrary statement an, if this statement is true, then it's true for the next one in the sequence. Then by induction, right? Because then you can start building like a ladder. Because if this statement is true, and you know this statement is true, then it must be true for n = 2. And if it's true for n = 2, it has to be true for n = 3, and so on and so forth. So you can say that an is true for all counting numbers. You also have proof by contradiction, aka the fun one, because this is assume not A. You do the logical consequences of assuming that A is false. And then you end up getting a logical contradiction somewhere, so you can say, all right, I hit a contradiction, therefore A must in fact be true. And then there's also proof by contrapositive, which I'm not going to talk about because I don't want to go into what a contrapositive is. That's a logic thing. I'm sure Aleph, given that he is a mathematician, definitely knows what it is. So you could ask him to talk about it. Yes, actually. It's funny you say that, Tyler. Yes, it is logic. There's a subset of philosophy that is just based on logic. Oh, interesting. Yeah. If you want Astral, I can explain it to you later if you want. Because that would be quicker. But yeah, so this is proving things is an application of the subset of philosophy of logic. But yeah, so to answer Tyler's original question, Gauss proved it one of these ways. I think specifically he ended up doing direct proofs. Like a really complicated direct proof. I did have to do it when I took vector calc, but that was years ago and I don't remember it. So Alright, back to what we were actually talking about. Nah, come on. Yeah, it's more like it. Alright. Theorem 3. The theorem for curls and integrals. Yes, the fields do share origins. Physics, specifically, used to belong to natural philosophy until the 1800s, I think, when they finally decided to declare physics like a field of science. Yeah. But okay, so the theorem for curls. If I take the surface area, the open surface area of the curl of a vector function, this ends up equaling the line integral of A dot dl. So what this means is, what this means graphically, right? If I have some open surface, S, and I want to take the curl, so I add up all the rotations of the vector field within this that lie on this surface. This is equivalent to just adding up the contributions of the vector field itself along the path defined by the boundary of the surface. That one's a bit kind of abstract. But it allows you to reduce a surface integral to a line integral, which is always fun. Less math. And so those are the three primary integral theorems for vector calculus. This one specifically is called, or at least I know it as, Stokes' law. Yeah. So yeah, any questions on anything I've covered today? So I will give you a hint, or a sort of like tease, sort of. Gauss's law. Oh, that is this one. Gauss's law is important for Gauss's law is very useful. Oh, come on, let me write. Yeah. So, Gauss's theorem, very important for electrostatics when you're talking about electric fields. Da, da, da. Stokes' law, very important for magnetostatics when we're talking about magnetic fields. And that is because, as you may have intuited, electric fields tend to come from a source. They tend to radiate outward, and they don't tend to rotate. They don't really have a rotation to it. Whereas magnetic fields do have a rotation to them and don't really come from a source or a sink. Yes, Nep will finally learn how magnets work. Ooh, yes, sorry. Thank you for reminding me. I want to do one more thing tonight. I want to show you how does a railgun work. Ah. Thank you, Astral, and thank you, Cyrano, for the hydrate. You want to do Metaflora? We'll do Metaflora after you learn how how a railgun works. That's your reward. All right. How does a railgun work? We can do both, Tyler. We can do both. So, let's suppose... I'm not good at drawing this. Alright. There we go. Let's say I have a resistor that's connected to two parallel rails. Metallic conductive rails. Yes, railgun does eat a chunk of metal super fast, but I want to show you why it does it, how it does it. And let's say I put a bar of metal across these two rails. This bar is moving with some velocity as a function of time. And it also has some constant... why did I do that? It has a constant mass, m. So, we want to know... Okay, the first thing we need to figure out... oh yeah, sorry. There are some other things I need to define. The distance between the rails is L. And I'm going to say there's a magnetic field that goes into the page. So this symbol that I just wrote just means that the vector, the magnetic field vector, is pointing into the page. Because obviously I can't show 3D like this is a 2D page. So yeah. Which means all the magnetic field vector lines point into the page, into this area. And I'm just going to assume it's a constant magnetic field. So, the equations we will need. Ohm's law. Simple enough. If you have a circuit, then the voltage in the circuit is equal to the current flowing through it times the total resistance. We have one resistor here, so that'll be super simple. The other thing we need. Why I introduced derivatives today. So, if you have a magnetic field that changes over, or if you have a magnetic field, this is called the magnetic flux. The magnetic flux is defined as the surface area of B dot dA, which we just introduced. This tells you how many magnetic field lines pass through an area. In this case, we want to know how much magnetic field passes through the area defined by this closed circuit given by like this path. Right? So, that's the magnetic flux. So, there's a theorem in electromagnetism that we will discuss far later, but again, I want to talk about how a railgun works, that states that if your magnetic flux changes in time at all, then it will induce a voltage that works to oppose this change in flux. This is called Lenz's law. So, if there is initially no current flowing through this circuit, but this bar is moving, which changes the area that the magnetic field passes through, then it will induce a voltage that will generate a current, right? So we can calculate this. So this B is constant, and like I said, the area vector we define as perpendicular to the surface, which makes it parallel to B. So it's parallel to B, which means I can get rid of the dot product. Because like we discussed last week, if the two vectors are parallel, then the dot product is maximum and just becomes the product of the magnitudes. So I'm going to drop the vector notation. And this just becomes an area integral. An area integral Actually, let me do this on a separate page. Oh, wait, No, I'm gonna do it this way. Sorry. I'm gonna erase this for a bit. So. So, because the area vector and the magnetic field vector is parallel, this just becomes the area integral of B times B with respect to dA. And because our area is a rectangle, this is just what we call the double integral of dx dy over the surface. Well, this B, I said, is constant. It's what we call uniform. So if I move anywhere in this area, the strength of the magnetic field doesn't change. And since it's constant, I can take it out of the integral. And so the integral, like I said, of a constant is just B times the area. So the area is given length times width. Yeah, length times width. Let's call this width. No, width. And since this is moving, the width is going to be increasing with respect to time. So this width is going to change. So phi b equals b times L times width as a function of time. All right. So now we can plug this into Lenz's law. So the induced voltage is going to be negative times the derivative with respect to time of B L times W. Well, the magnetic field and L are constant. So again, we can take them out of the derivative. B L dW dt. Okay. This is getting out of hand. All right. What the? Oh, okay. B equals negative B L dW dt. Well, okay. If we go back to our diagram, the change of this distance with respect to time is just the velocity. Change of position over time is velocity. So this equals negative B times L times your velocity. Cool. Now we know the voltage in the circuit, but we want to know the current that's flowing through the circuit. So we use Ohm's law. So that tells us that the current is just equal to the induced voltage over the resistance, which is simply BLV over R, script V. So the next part we need to figure out, so okay, the end goal of this problem, right? If I'm designing a railgun, I want to know how fast it's going to go. How fast can it actually get by the time it stops having contact with the rails? So that means we actually need to figure out what this velocity is as a function of time. So that's what we're building up to. So the next part is we need to figure out so another thing to note about magnetostatics. If you have a magnetic field acting on a current carrying wire, there will be a force on that wire. No, Tyler, what are you talking about? This is just a fun backyard project. So, the force on the rod, because now a current's flowing through it because the induction, is going to be the current times the length of the circuit that the current's flowing through, cross product the magnetic field. But right now, I only care about the magnitude of the force, so we can just use the formula I brought up last week. Sine theta, where theta is the angle between the circuit path and the magnetic field. Well, the circuit path, if I bring back the diagram, is along the page, right? It's in the XY plane. The magnetic field, which is going into the page, is perpendicular to the XY plane. So that means we have sine of 90, and it is in fact just the current times the length of the path times b. Well, so in this case, since we only care about what it's doing to the bar itself, then this length that we care about is actually only the length of the bar, which is L. So actually I don't have to write anything else. All I need to do is substitute in the current that we just calculated. So this ends up equaling minus b squared L squared V over R. That is the force on the bar. As a function of time. So remember, this velocity is going to change in time. All right. Okay. So we have the force. And I'm going to make it positive because, like I said, I only care about the magnitude. Oh, Metafloor is bullshit today? Alright. We can still do Metazoa, though, after this. I bet it's Chinchilla. But I'll start with Wombat. Okay. So, if you remember from high school physics, Newton's second law, F equals ma. So this quantity equals ma. The mass of the rod times the acceleration of the rod. Well, acceleration is the change of velocity with respect to time. So that's dv dt. So that tells us that the change in velocity with respect to time is directly proportional to the velocity itself. Yeah, but you got a cool tattoo to show for it. Alright. If you have an equation that includes some function and its derivative, that is what we call a differential equation. Which V has, or not V. That's another one of Z's alter egos. Z has talked about differential equations on her channel. I don't think she's actually gone into how to solve every kind of differential equation, but I think she talks about a bit more about what they mean in physics. So I'm gonna forego that for now and just solve this. So that becomes V equals V naught times E to the B squared L squared T over R, where E is Euler's number. This is an exponential. This tells us that the velocity of this rod increases exponentially. And it scales as the exponential of the length of your rail squared. So for instance, let's say for instance, if we doubled the length of our rail, then that means our velocity over time ends up becoming e to the fourth times, like, it ends up increasing by a factor of e to the fourth, which, if I use a calculator, because I'm not doing that in my head, that is, okay, that is almost 55 times the velocity of half the length of the rail, or the initial length of the rail. That is insane. That is how efficient railguns are. Same thing happens if you double the magnetic field, although you start getting heating issues because to generate that magnetic field takes a lot of energy. But yeah, that's how a railgun works. In essence. Obviously, this is a very simplified model, but yeah. Any questions about railguns?